Hello everyone. In this AV, we would be taking up the chapter Heat Engine, the second law of thermodynamics. Now, you already know the first law of thermodynamics, which states that when a small amount of heat is given to a thermodynamic system, some part of it will be used to increase the internal energy of the system and some part of it will be used to do the work. Now, this law had some limitations which gave the need for the second law. Firstly, the first law of thermodynamics talks about the complete conversion of work to heat, but it did not tell us the conditions under which such conversions are possible. This was the first limitation. The second limitation of the first law of thermodynamics was whether the thermodynamical system does work or it gains or loses heat. It doesn't make any difference between heat and work. And finally, the first law of thermodynamics doesn't indicate the direction of flow of heat. Now, these limitations led to the second law of thermodynamics. Now, we have two statements for the second law of thermodynamics. Basically, the first one is Kelvin-Planck's statement, which states that it is impossible to convert all the heat extracted from a hot body into work. So basically it means that all the heat energy which is supplied to a system cannot be converted into 100% of work. And in other words, we can also say that all the heat taken from a body will not be converted to work, and some part of the heat will have to be given to the colder body. And the next statement was given by Clausius. So it states that it is impossible to transfer heat from a cold body to a hot body without expenditure of work by an external energy source. Now, this is what we see in refrigerators. So until and unless we have an external working energy or working source, we cannot transfer heat from a colder body to the hotter body. Now, the second law of thermodynamics cannot be proved directly. The main evidence or the only proof for its truth is that no machine that has ever been designed could work in contradiction to this law. That is why the second law of thermodynamics stands verified, and the deductions made from this law are found to agree with the practical facts. So now we will see and talk about the heat engine and its efficiency. Now, heat engine is basically a cyclic device by which heat is converted into work or heat is converted into mechanical work. When we try to understand this heat engine, the heat engine has got three parts. Basically, the source, which is at a higher temperature T1. Then we have the working substance. Then we have the sink, which is the colder body and is at a lower temperature T2. Now, this source is also known as hot body or hot reservoir, and sink is known as the colder body or cold reservoir. Now, the working of this heat engine is, we assume that the working substance take Q1 amount of heat from the source, which is at the temperature T1. Here what we have to keep in mind is the source and the sink, they maintain the temperature T1 and T2, and they don't change this temperature. What I mean by this is the source was at T1 temperature and the working substance has taken Q1 amount of heat from this source. Still, after giving Q1 amount of heat to the source, to the working substance, the source still remains at T1. It's like we are taking one bucket of water from the ocean and it doesn't affect the ocean. The ocean remains the same. So similarly here, Q1 amount of heat has been taken from the source and source still remains at the temperature T1. Now, the working substance obtains the work W and rejects the remaining amount of heat to the sink, and that remaining amount of heat is Q2. Now the sink is at temperature T2 and T2 is smaller than T1. Now after getting this heat Q2, still the sink will remain at the temperature T2 only. Now if we have to find out what is the work done, then from first law of thermodynamics we know that the work done is given as W is equal to Q1 minus Q2. This is the work done by the heat engine. Now the efficiency of the engine, which is denoted as eta, is defined as the ratio of the work done, total work done or net work done in one cycle by the amount of heat taken from the source for this one cycle. Now we can substitute the value of W, which is Q1 minus Q2, and denominator we have Q1. So this can be written as, if we write the denominator separately for both the numerators, then we have eta or efficiency of the heat engine, efficiency to be equal to 1 minus Q2 upon Q1. Now using that formula Q equal to MST, we can prove that this is also equal to 1 minus, instead of Q2 by Q1 we can write it as T2 by T1. So the efficiency of the heat engine is given as 1 minus Q2 upon Q1 or 1 minus T2 upon T1. Here what we have to note is this equation of efficiency is independent of the working substance. And the second thing is, the efficiency of any engine can never be 100%, because if we want it to be 100%, it would mean that there should be no heat rejected to the sink. That means T2 should be 0, which is not possible. Now Carnos developed a theoretical plan of an idealized heat engine, and he assumed that it is free from imperfectness which is there in the actual engine. Things like friction was not considered. So this engine is an idealized heat engine, which is practically not possible. So we assume that these are the parts, and we assume that it will undergo expansion and compression, and through the graph we will see the steps. Now here we have the 4 components of the Carnos ideal heat engine. First part is, or the first component is the working substance. What we see here is the walls of this working substance is perfectly insulated. There is the working substance, that is a gas or we can say that it's an ideal gas, and there are certain weights placed on the piston. This piston is perfectly insulating and it is frictionless. Now the walls of the cylinder are also insulated. Only the base of the cylinder is conducting, and we have certain weights placed on the piston. The second component of the Carnos ideal heat engine is a hot body or the source, which is at a temperature T1. Now this source or the hot body or the hot reservoir has infinitely large heat capacity, and the temperature T1 will remain constant, as we discussed in the previous case. Then the next component is the heat insulating stand, and finally the fourth component is the cold body or the sink, which will have a constant temperature of T2. No matter how much heat it takes, it will still maintain the temperature T2. So now let's find out how it works and what we do. Now cylinders, this cylinder will be placed on these bodies one after the other, and then we will see the graph. Now at first what happens is the cylinder is placed on this hot body or the source, which is at the temperature T1, and a PV diagram is made, which is basically a graph. So once this substance is placed on this hot body or the source, and slowly some of the weights are removed. Now the moment it is kept here, as we discussed that the bottom or the base is conducting for this cylinder. So when it is placed on the hot body, heat is being absorbed in this by this gas. So this gas, after getting the heat, will expand, and once the gas expands, this piston will be pushed upwards. That means some work has been done, and since heat has been allowed to enter, this process will be isothermal expansion of the gas. So when we draw the PV diagram, from point A to point B is isothermal expansion. Please remember, it's isothermal because heat has been allowed to enter the cylinder from the source, and the gas has expanded doing some work. The temperature is T1. So this first step is being depicted or shown by point A to B. Now what we do is we take this cylinder and place it on heat insulating stand. Now this is heat insulating stand, and this will not allow any of the heat to enter or to come out of the cylinder, and we again remove the weight very slowly. Now what happens is, once the weights are removed, the gas will further expand. Once the gas expands, the substance does work in raising the piston again, and its temperature will decrease. But here we did not allow any heat to come out of the system or to get into the system. So that will be adiabatic expansion. Now this is being depicted in the PV diagram by point B, C. So initially when we placed it, it was at temperature T1. Adiabatically expansion was made. So the gas did the work in pushing the piston, but the temperature dropped from T1 to T2. Now the second step is shown by the points B, C. The third step is, what we do is, we place the cylinder from heat insulating stand on to the cold body or the sink, which is at the temperature T2. And what we do is, now we put back the weights in very small steps. Now, since the base of the cylinder is conducting, and here this wall of the sink is also allowing the heat exchange, so the process will be isothermal, and since we have placed the weight, the gas will be compressed until we reach a state which is represented by point D. And the isothermal compression will take place at a constant temperature T2, which is the temperature of the sink. Now in this process, or during this process, the work is done on the substance by the piston, and the heat which is developed will be given out to the sink. So this is represented by the point CD. It is isothermal compression and the temperature remains T2 only. Now finally what we do is, we place the cylinder from the sink again back to the heat insulating stand, and further certain weights are placed on it. Now some more amount of work is done on the substance and it's compressed adiabatically. So here its temperature rises, and this process will be continued till the temperature rises once again to T1. That means till we reach point A from where we started. So this is represented by the point DA. This is adiabatic compression from T2. It has been compressed and it reaches the temperature T1, which is represented by the point DA. Now the efficiency of this Carnos ideal heat engine is again given by efficiency eta is equal to 1 minus Q2 upon Q1, or is equal to 1 minus T2 upon T1. So what we mean to say here is, the efficiency of this ideal heat engine or Carnos heat engine is again independent of the working substance. And since in this graph this is a cyclic process, so this process can be started from any point and can be reached back to that point only. So as they have mentioned that the efficiency of Carnos reversible engine is independent of the working substance and depends only upon the temperatures of the sink and the temperature of the source. Now to have 100% efficiency for the engine, this efficiency, the value should be 1. And if we want the value of this efficiency to be 1, that means T2 should be 0, which is not possible. That is why practically we do not have any engine which has got 100% efficiency. Now Carnos engine has two ideal features which cannot be achieved in practicality. Firstly, the working substance cannot use the full temperature difference available between the source and the sink. And secondly, each process in the Carnot cycle is completely reversible, which is again practically not possible. That is why in practical reality, this is, or the Carnot's ideal heat engine is not possible to obtain. Now just the opposite or reverse of heat engine is Carnot's ideal refrigerator or heat pump. So we will try to understand this, which is just the opposite of the heat engine, or we can say that it is a heat engine running in backward direction. Now in refrigerator, again we have three substances: the hot body, which is at the temperature T1, the working substance, and the cold body, which is at the temperature T2. Now in refrigerator, what happens is the working substance takes in heat from the body which is at lower temperature, that is, it takes heat from the colder body which is at the temperature T2, and it takes Q2 amount of heat. Then a net amount of work is done on the working substance by an external agent, and then this working substance gives a larger amount of heat to the hot body, which is Q1. Q1 is the larger amount of the heat, and this is possible because the working substance has been helped or has been worked on by an external agent. Now it continuously transfer heat from a cold body to the hot body at the expense of mechanical work or mechanical energy supplied to it by the external agent. So this working substance is known as the refrigerant. Now again, in this ideal refrigerator or heat pump, each step is reversible. Therefore, even it is possible to reverse the entire cycle. So here also the work done would be Q1 minus Q2, and in this case, that is for refrigerators or heat pumps, we do not call the efficiency, we call it as coefficient of performance, and we write it or denote it as K, not eta anymore, like in case of the ideal heat engines. So this is defined as the measure of the performance of the refrigerator. So we call it as coefficient of performance, and it is the ratio of heat taken. So we are taking heat from the colder body, that is Q2. So it is the ratio of the heat taken to the work needed to run the refrigerator. So Q2 by W. Now again we can put the value of W, that is Q1 minus Q2. So if we put the value of W, we have this equation. So if we write it separately, then we have K equal to Q2 by Q1 minus 1, or we can simply leave it here, or we can convert this into the equation for T1 and T2. So that would be T2 by T1 minus T2. So this is the expression for coefficient of performance for the refrigerators. Now let's look at a few numericals. Suppose this question says a Carnos engine working between 0 degrees Celsius and 100 degrees Celsius takes up 746 joules of heat from the source per cycle. Calculate number 1, the work done by the engine, number 2, heat rejected to the sink, and number 3, the efficiency of the engine. So here we have been provided with T1, T2 and Q1. So we know that if an engine takes in heat Q1 from the source, which is at the temperature T1, does some work W, and then rejects the remaining heat to the sink, that is the heat rejected is Q2 and the sink is at temperature T2, then we know that the efficiency is given as 1 minus T2 by T1. So here let's write the given things first. So here we have written the given things, that is T1, which is given as 100 degrees Celsius. We have converted it to Kelvin by adding 273 to it, and it comes to 373 Kelvin. Temperature T2 is given as 0 degrees Celsius. If we add 273 to it, we get 273 Kelvin, and Q1, the value of Q1 is given as 746 joules. Now at first we have to find out the work done. Now we know that the efficiency eta is W by Q1, or this is also equal to 1 minus T2 upon T1. If I just consider this part of the equation, then from here this implies that work done is nothing but efficiency into Q1. Now the value of efficiency we have to calculate, but we know that efficiency is also equal to 1 minus T2 upon T1, and the value of T2 and T1 and Q1 we already have been provided with. So I'll just change this and we will write it as, instead of efficiency we will simply write 1 minus T2 upon T1 multiplied by this Q1. So we simply substitute the value and we have W is equal to 1 minus T2 is 273 Kelvin by T1 is 373 Kelvin multiplied by Q1, that is 746 joules. Now when we solve this, we will get 373 minus 273 upon 373 multiplied by 746, and after calculation this comes out to be equal to 200 joules. So this is the solution for the first part, that is the work done by the engine per cycle. Now the next part of the question is to find out the heat rejected to the sink. Now heat rejected to the sink is Q2. We have seen that Q2 amount of heat is being rejected. So we know that W is equal to Q1 minus Q2. So from here we can find out Q2, which is nothing but Q1 minus W. We have the value of Q1, that is 746 joules. So we write 746 minus, and we have calculated the value of W, that is 200 joules. So 200. Now 746 minus 200 is 546 joules. That is the answer for number 2. And finally we have to find the efficiency, and that we have to find it in percentage. So the third part, where we have to find the efficiency. So efficiency percentage is given by eta is equal to W by Q1, and since we have to find the percentage, we will multiply it with 100. Now work done we have already calculated here, that is 200 joules. So we write it as 200 joules divided by Q1, that is 746, and we multiplied it with 100. So this will come out to be 26.8%, and that is the solution for the third part. Now this question is based on refrigerator or heat pump. It says that a refrigerator is to maintain eatables kept inside at 9 degrees Celsius. If the room temperature is 36 degrees Celsius, calculate the coefficient of performance. So here we have to find out K, that is the coefficient of performance, which is given as K equal to T2 by T1 minus T2. So first what we do is we convert the temperature which is given to us in Celsius to Kelvin. Now here T1 is the temperature of the hot body, so that is 36 degree Celsius, or which is equal to 36 plus 273, that would be 309 Kelvin. Now the temperature T2, or the temperature of the cold body, is 9 degree Celsius. Now if we convert it to Kelvin, 9 plus 273, so that is equal to 282 Kelvin. Now we know that the coefficient of performance, that is denoted as K, is equal to T2 upon T1 minus T2. So we have the values, we simply substitute. T2 is 282 Kelvin and T1 is 307 minus T2 is again 282. So it would be 282 upon 27. So that is, both are in Kelvin, and since this is the coefficient of performance, So there will be no unit and nearing 10.4. So the value for K here is 10.4. This is the answer, and that's all in this AV. Thank you so much.